Welcome to this problem walkthrough. Today, we'll explore problem number 1624, largest substring between two equal characters. We'll discuss the problem requirements, analyze the brute force approach, and break down the solution step by step. Let's dive in. The goal is to determine the length of the largest substring that exists between two identical characters in the string. In this problem, you're tasked with analyzing a string, which consists only of lowercase English letters. Specifically, if you have two matching characters at positions I and j, where I is less than j, the substring of interest lies between these two positions, meaning it starts at I+1 and ends at j1. The length of this substring is calculated as ji1. If the string does not contain any repeated characters, the result should be -1. The input is a single string with a length between 1 and 10,000 characters, and the output is an integer representing the desired length or -1 if no such substring exists. For example, consider the input string abca. Here, the character appears twice, at indices 0 and 3. The substring between these two occurrences is bc, which has a length of 2. Therefore, the output for this input is 2. On the other hand, for the string cbzxy, no character appears more than once. As a result, there are no substrings to evaluate, and the output is -1. These examples demonstrate the two possible outcomes, either finding the length of the largest substring or returning -1 when no repeated characters exist. Now, let's examine another example to solidify the concept. Take the string kabak. Here, the character C appears twice, at indices 0 and 5. The substring between these positions is abba, which has a length of 4. This is the largest substring between two equal characters in this string, so the output is 4. Additionally, the problem comes with a few constraints. The string length will always fall within the range of 1 to 10,000 characters, and the input will only consist of lowercase English letters. This ensures that the problem is well-defined and computationally feasible. When analyzing edge cases, consider the following scenarios. If the string contains only one character, like a, there are no repeated characters, so the output should be -1. Similarly, if all the characters in the string are unique, such as in ABC, there are no substrings to evaluate, and the output is again -1. On the other hand, if the string consists of repeated instances of the same character, like AAA, the substring between the first and last occurrence of the character should be considered. Finally, since the string length can be as large as 10,000 characters, it's important to ensure that your solution is efficient and can handle the maximum input size without running into performance issues. To solve this problem, we first consider the brute force approach. The intuition here is straightforward. We systematically examine all pairs of identical characters in the string. Using two nested loops, we check every possible combination of characters. The outer loop iterates through each character in the string, while the inner loop searches for the same character later in the string. Once we find a matching pair, we calculate the length of the substring between them using the formula ji1, where I and j represent the indices of the first and second occurrences of the character, respectively. By repeating this for all possible pairs, we can determine the maximum length of such substrings. However, this approach requires checking every pair, resulting in a time complexity of n squared. To optimize, we can instead utilize a single traversal of the string combined with a hash map. The hash map helps us track the first occurrence of each character, allowing us to compute the substring length in constant time for subsequent matches. The optimized approach is more efficient and relies on a clear sequence of steps. First, we initialize an empty hash map to store the first occurrence of each character. Then, as we traverse the string, we check each character one by one. If the character is not already in the hash map, we store its index as the first occurrence. If the character is already in the hash map, we compute the substring length using the formula current_index, first_occurrence 1. At this point, we update the maximum length if the new substring is longer. By the end of the traversal, we return the maximum length found. This method is highly efficient, with a time complexity of n, since we only traverse the string once, and the hash map operations are performed in constant time. The key insight here is understanding that the substring length depends solely on the first and last occurrence of a character, making hash maps a natural choice for efficiently tracking these indices. By eliminating the need for nested loops, we achieve a linear time solution, which is critical for handling larger input sizes. Given the options, the optimized approach is the clear choice due to its efficiency and simplicity. While the brute force approach can be easier to understand conceptually, its n² complexity makes it impractical for larger strings, especially when n can go up to 10 to the power of 4. In contrast, the optimized approach, with its n complexity, is far more scalable. By leveraging hash maps, it solves the problem in a single traversal, making it not only faster but also more elegant. When comparing the two, the brute force method is simpler to implement but quickly becomes inefficient as the input size grows. On the other hand, the optimized approach, though slightly more complex to implement, provides a significant performance advantage for larger inputs. Ultimately, the decision to use the optimized approach is driven by its ability to handle large datasets effectively, ensuring both speed and practicality in real-world scenarios. To solve this problem, we need to identify the maximum length of a substring where the first and last characters are the same. If no such substring exists, we simply return 0. Let's first look at the brute force approach to solving this. We start by initializing a variable max_length to 0, which will keep track of the largest substring length we've found. The input is a string s of length n, and our goal is to find the output, which is the maximum length of the substring satisfying the conditions. The process begins with an outer loop that iterates over each character in the string using an index I. This loop allows us to select each character as a potential starting point for a substring. For example, in the string apka, we start with the character at index 0, which is A, and then proceed to the next character B at index 1, and so on. Once we've selected a starting character, we use an inner loop to examine all subsequent characters in the string to determine if there's a match with our chosen character. The purpose of the inner loop is to check whether the character at our starting index I matches any of the characters at positions j that come after it. This is done by iterating from I+1 to n, where j represents the current index being checked. If the characters at s, I, and s, j match, we then calculate the length of the substring between these two positions, which is given by j I+1. If no match is found, we simply continue iterating to check the next character. Whenever we find a matching pair, we compare the calculated length with our current max_length. If the new length is greater, we update max_length to reflect this value. This ensures that we always keep track of the longest substring identified during the process. By the end of the nested loops, max_length will contain the length of the largest valid substring found so far. After completing all iterations, we return the value of max_length as our result. It's important to understand that while this brute force approach is straightforward to implement, it has a time complexity of n² due to the two nested loops. This means that as the length of the string increases, the algorithm becomes increasingly inefficient. In the worst-case scenario, where every character in the string matches with every other character, the number of comparisons can grow significantly. This inefficiency arises from redundant checks, such as comparing the same pair of characters multiple times. For instance, if we've already checked S0 against S3, there's no need to check S3 against S0 again. To address these inefficiencies, we can optimize the approach using a hash map, which allows us to track the first occurrence of each character and avoid repeated comparisons. In the optimized approach, we use a hash map, or dictionary, to store the first occurrence of each character as we iterate through the string. The dictionary's keys represent the characters, while the values represent their first occurrence indices. By doing this, we eliminate the need for nested loops. Instead of checking every possible pair of characters, we can determine whether a character has been encountered before in constant time. During the traversal, if a character is not in the dictionary, we store its current index as its first occurrence. If the character is already in the dictionary, we calculate the length of the substring between the current index and its first occurrence. This length is given by current_index, first_occurrence plus 1. As we calculate these lengths, we update the max_length variable to ensure that it always holds the largest value encountered so far. This approach significantly reduces the computational overhead compared to the brute force method. To implement this optimized approach, we begin by initializing two variables, max_length, set to 0, and first_occurrence, an empty dictionary to store the first occurrence of each character. We then traverse the string, examining each character C at index I. If C is not already in the first_occurrence dictionary, we store its index I. If it is in the dictionary, we calculate the substring length as I first_occurrence, C, plus 1 and update max_length if this new length is greater than the current value. After completing the traversal, the value of max_length will represent the length of the largest valid substring. This approach has a time complexity of O(n) due to the single traversal of the string and the constant time operations for dictionary access. This makes it a much more efficient solution for larger strings. The brute force implementation, while simple, can be replaced with this optimized approach for better performance in real-world scenarios. This code solves LeetCode problem 1624, largest substring between two equal characters, by efficiently finding the maximum length of a substring where the first and last characters are the same. The solution uses a dictionary to track the first occurrence of each character as it iterates through the string. The algorithm starts by initializing an empty dictionary, first_occurrence, to store the first index where each character is found. It also initializes max_length to -1, which is used to track the maximum length of valid substrings, or -1 if none exist. The loop iterates through the string with enumerate, capturing both the index I and the character char at each step. For each character, the code checks if the character already exists in the first_occurrence dictionary. If it does, this means a substring can be formed between the current index I and the first occurrence of the character. The length of this substring is calculated as I first_occurrence, char 1. The max_length is then updated to be the maximum of its current value and the length of this substring. If the character does not exist in the dictionary, it is added, with its value set to the current index I. This ensures that only the first occurrence of each character is stored, which is critical for calculating the correct substring lengths. Finally, after processing all characters, the function returns max_length. This represents the length of the largest valid substring found, or -1 if no such substrings exist. The algorithm runs in O(n) time, where n is the length of the string, making it very efficient for large inputs. This is the Java implementation of LeetCode problem number 1624. Largest substring between two equal characters. The logic mirrors the provided Python version, with key differences such as the use of a hash map for character tracking, explicit type declarations for variables, and the Java class structure. The method iterates through the string, storing the first occurrence of each character and calculating the maximum substring length between matching characters. If no valid substring is found, it returns -1. This approach ensures clarity and efficiency in Java. To solve this problem, we start by initializing two key components, a dictionary called first_occurrence and a variable called max_length. The dictionary will help us track the first index where each character appears in the string, while max_length is initialized to -1 and will store the largest substring length between two equal characters. Now, as we begin iterating over the string s equals apka, we first encounter the character at index 0. Since it is not in first_occurrence, we add it to the dictionary with its index, at 0. At this point, no substring can be calculated because there's no second occurrence of a. Moving forward, the character b at index 1 is also not in the dictionary, so we add it, at 0, b1. The same happens for the character c at index 2, which gets added as a 0, b1, c2. Still, no substrings can be calculated yet since no character has repeated so far. When we reach index 3, we encounter the character at again. This time, a is already in first_occurrence, and its first occurrence is at index 0. This allows us to calculate the length of the substring between these two occurrences using the formula current_length equals I first_occurrence, char 1. Plugging in the values, we get current_length equals 301 equals 2. We then update max_length to the maximum of its current value and current_length, resulting in max_length equals max, -1, 2, equals 2. This gives us the largest substring length for this example. The final output for the input s equals apka is therefore max_length equals 2. Now, consider a simpler example where s equals AA. We initialize the same components, first underscore occurrence equals, and max underscore length equals -1. At index 0, the character is not in the dictionary, so we add it as a 0. Again, no substring can be calculated at this stage. Next, at index 1, we encounter the character a once more. Since it is already in first underscore occurrence, with its first occurrence at index 0, we calculate the length of the substring between these two occurrences. Using the formula current underscore length equals I first underscore occurrence, char, 1, we get current underscore length equals 1, 0, 1 equals 0. Updating max underscore length to the maximum of its current value and current underscore length, we find max underscore length equals max, minus 1, 0, equals 0. This means the largest substring between two equal characters in S equals AA has a length of 0, as the two characters are directly adjacent. Finally, let's consider an example where no characters repeat, such as S equals ABCD. As usual, we start with first underscore occurrence equals, and max underscore length equals -1. At index 0, the character A is added to the dictionary as a 0. No substring can be calculated yet. At index 1, the character B is added to the dictionary, resulting in a 0, B, 1. Similarly, at index 2, C is added as a 0, B, 1, C, 2, and at index 3, D is added as a 0, B, 1, C, 2, D, 3. Throughout the iteration, no character appears more than once, so no substrings can be calculated. As a result, max underscore length remains -1, indicating that no valid substrings exist in this case. To summarize, this algorithm uses a dictionary to efficiently track the first occurrence of each character. For every subsequent occurrence of a character, the length of the substring between its first and current positions is calculated and compared to the current maximum. If no repeating characters are found, the result remains -1. This approach ensures the solution is both clear and efficient. The time complexity of this solution is determined by the single for loop that iterates through the string S. If the length of the string is n, the loop runs exactly n times, processing one character per iteration. Inside the loop, we perform dictionary operations that include checking if a character exists, adding new entries, and retrieving values. All of these operations are constant time, or O1, on average because dictionaries in Python use hash tables. Similarly, updating the max underscore length variable involves the max function, which is also an O1 operation. Since all operations within the loop are O1, and the loop itself executes n times, the overall time complexity of the solution is O(n). This ensures that the algorithm scales linearly with the size of the input string. To analyze the space complexity, we look at the additional memory used by the solution. The main contributor is the first underscore occurrence dictionary, which stores the index of the first occurrence of each unique character in the string. In the worst case, such as when all characters in the string are unique, the dictionary will store up to n entries, one for each character. Each entry in the dictionary consists of a key, which is a character, and a value, which is an integer index. Since the memory required for each entry is constant, or O1, the total memory used by the dictionary is proportional to the number of unique characters, making it O(n). Additionally, the loop variables and the max underscore length variable require constant space, or O1. Therefore, the total space complexity of the solution is O(n), driven primarily by the dictionary storage. The solution performs efficiently across all cases, whether best, average, or worst. In the best case, where all characters in the string are unique, the dictionary still stores all n characters, and the loop runs n times. The time complexity remains O(n), and the space complexity is also O(n). In the average case, where the string has some repeated characters, the dictionary might store fewer entries, but the loop still iterates over all n characters, so the time complexity remains O(n). The space complexity is unaffected as it depends on the number of unique characters. In the worst case, when the string is long or has many unique characters, the dictionary stores all n characters, and the loop completes n iterations. The time complexity remains O(n), and the space complexity is O(n). By contrast, a brute force approach, which examines all pairs of indices, I, j, to find matching characters, would require two nested loops, resulting in O(n)² time complexity. While the brute force approach uses O(1) space, the optimized solution achieves a much better time complexity of O(n) by using a dictionary to eliminate nested loops. To formally prove the solution's big O complexity, let the length of the string be n. The for loop is the main contributor to the time complexity, running exactly n times. All operations inside the loop, such as dictionary insertions, lookups, and updates, are O(1) on average due to the hash table implementation of Python dictionaries. This means the total time complexity is O(n), because the loop dominates. For space complexity, the dictionary stores at most n entries, one for each unique character in the string. Since each entry requires constant space, the overall space complexity is O(n). Compared to a brute force approach, which has O(n²) time complexity and O(1) space complexity, this solution is significantly more time efficient while maintaining reasonable space efficiency. Thus, the algorithm is well optimized for both time and space, making it a robust solution to the problem. When solving this problem, there are a few common mistakes that you'll want to avoid. First, forgetting to handle edge cases is a frequent pitfall. For instance, if the string has no repeating characters or consists of just a single character, your algorithm might break or produce incorrect results. Testing edge cases like empty strings, minimal inputs, or very large inputs is crucial to ensure robustness. Next, relying on inefficient nested loops to compare all pairs of characters is another issue. This approach results in a time complexity of O(n²), which is often too slow for larger strings where n can go up to 10,000 or more. Lastly, mismanaging indices, such as incorrectly calculating substring lengths or accessing out-of-bound indices, can lead to subtle bugs. Double-checking your index calculations is essential to avoid these errors. Another mistake to watch out for is ignoring the problem's constraints. For example, while the problem might specify that the input consists of lowercase letters only, assuming this without validating the input can lead to undefined behavior if unexpected cases arise during testing. It's always a good practice to validate or sanitize inputs where needed. Additionally, overcomplicating the solution is a trap many fall into. Using unnecessary data structures, like trying to manage substrings with complex hash maps when simpler methods would suffice, can make your solution harder to understand, debug, and maintain. Striking the right balance between simplicity and efficiency is key to writing clean, effective code. Now, let's focus on some interview-specific insights. A lot of substring or character-based problems, like this one, can be approached using common patterns such as sliding windows, hash maps, or prefix sums. Recognizing these patterns early can save time and guide you towards optimal solutions. It's also important to communicate your thought process clearly. Walk through your handling of edge cases and explain the reasoning behind your algorithmic choices. This clarity is highly valued by interviewers. Be prepared to discuss trade-offs as well, like when a linear solution requires extra memory, while a slower quadratic approach might save on space. Always aim for optimal solutions after discussing brute force approaches, as interviewers often assess your ability to refine and optimize your ideas. Finally, practicing related problems, such as longest substring without repeating characters or subarray sum equals k, can deepen your understanding of these techniques and prepare you for similar challenges. Lastly, let's discuss some alternative approaches you might consider. The sliding window technique is a popular choice here. By maintaining a window to track the current substring, you can dynamically expand and contract it based on the problem's conditions. This reduces the time complexity to O(n), but you'll need to carefully manage the window boundaries to avoid errors. Another approach involves using a hash map to store the last seen index of each character. This allows for efficient updates to the start of a valid substring and simplifies the logic, though it does increase space complexity to O(n). Finally, prefix sum or array techniques can be helpful in certain scenarios. These methods involve pre-computing values like cumulative sums to make substring queries more efficient. While particularly useful for numeric problems, they may not always be directly applicable to string-based questions. Choosing the right approach often depends on the specific constraints and trade-offs required by the problem. Great job completing the walkthrough for problem number 1624. To recap, we discussed the largest substring problem, used a brute force approach, and reviewed its key aspects. Remember to practice identifying patterns and edge cases to improve your problem-solving skills. Thanks for watching. and we'll see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!